Hello everyone! In this video, we will be introducing the concept of copula. Throughout this tutorial, in addition to providing a basic introduction to copula, we will be utilizing a real-world dataset and demonstrating, using Python, how copula can be employed for data analysis. First, let's define what a copula is. A copula is a statistical tool that enables us to understand the relationships between multiple variables. In traditional multivariate analysis methods, it is often assumed that different variables follow the same distribution, such as a Gaussian distribution. However, with copula, we have the ability to decouple the marginal distributions from the joint distribution. This concept may be challenging to grasp initially, so let's use this diagram for further illustration. We are interested in understanding the correlation between x and y. To begin, we can examine their individual marginal distributions. For instance, x might follow a distribution that resembles a gamma distribution, while y might follow a distribution that resembles a Weibull distribution. Clearly, neither distribution is Gaussian, so traditional multivariate analysis methods are unsuitable for this scenario. Furthermore, it is evident that the relationship between x and y is nonlinear. Consequently, we cannot rely on simple linear regression to model this relationship. In such a situation, copula proved to be a suitable tool for research and analysis. A crucial point we mentioned about copula is their ability to separate the influence of the marginal distributions. How is this achieved? The separation is accomplished using the probability integral transform. The key idea of this transform is to convert the distribution between variables into a standardized space defined on the interval from 0 to 1. This transformation is achieved using the cumulative distribution function for each variable. After this transformation, we effectively remove the influence of the marginal distributions. This process reveals the dependency structure between the two variables. A copula is used to represent the joint distribution and describe the dependency structure with mathematical functions. This concept can be further clarified using Copula Theory, particularly through Sklar's theorem, which expresses it mathematically. This theorem states that the joint distribution of all variables represented on the left-hand side of the equation can be decomposed into the marginal distributions of each individual variable. After the probability integral transform, we can select a suitable copula function to represent the dependency structure in the joint distribution. That concludes our introduction to the basic theory underlying copula. Now, let's examine the scenarios and conditions where copula are especially suitable for analysis. We can summarize these situations with three main points. The first point emphasizes that copula are highly appropriate for multivariate data analysis. In real-world scenarios, different variables often exhibit distinct marginal distributions. Secondly, copulas are particularly suitable for modeling nonlinear dependencies between variables. Lastly, copulas are valuable for simulating and understanding extreme phenomena, making them ideal for such applications. Now, let's explore how to apply copula in practical scenarios. We also need to select an appropriate copula model to effectively simulate our observed data distribution. Here, we introduce two of the most commonly used copula families in research and practice. The first family is the elliptical copula family, which includes the Gaussian and student T copulas. A key characteristic of this family is its suitability for modeling symmetric data distributions. The student T copula is especially suitable for modeling extreme events and tail dependencies. For example, in finance, the student T copula can simulate the relationship between the stock prices of two companies in the same industry. When market conditions are favorable, the stock prices of both companies may rise together. Conversely, when market performance is poor, the stock prices of both companies may decline together. The second family is the Archimedean copula family. Within this family, there are three commonly used models: the Gumbel copula, the Clayton copula, and the Frank copula. The Gumbel copula is suitable for situations where your data exhibits upper tail dependence, such as in the analysis of rainfall events, where heavy rainfall often coincides with high river flow. The Clayton copula, on the other hand, might be used to represent drought conditions. When there is minimal rainfall, the reservoir water level will also tend to be relatively low. The third model is the frank copula, which is a symmetric type of copula. However, it is typically employed to depict moderate dependency between variables. This means that if your data distribution lacks strong tail dependence, the frank copula is a suitable choice. For each copula mentioned, I've provided an illustrative example. This information is for your reference. Due to time constraints, I won't go into the details. Next, we will use real-world data for copula analysis. To start, I'll provide a brief overview, including the background of the dataset. This dataset comes from the Birmingham area in the UK, covering summers from 2005 to 2017, spanning 12 years. During this period, there were 167 recorded convective storm events, each with corresponding rainfall radar data. These data are analyzed using a cell tracking algorithm, allowing us to identify the convective rain cells linked to each event. Convective rain cells are characterized by rainfall intensity and shape parameters. Here, we provide a visualization of a rain cell, specifically a convective rain cell constructed from a theoretical model. The shape of a convective rain cell is generally approximated as an ellipse, characterized primarily by its major and minor axes. At the center of the cell is where the heaviest rainfall typically occurs. Therefore, the dataset we are utilizing today includes these key parameters for each rain cell. The first parameter is the maximum rainfall intensity within the cell, while the second and third are the corresponding major and minor axes of the cell. This data is available in the CSV file located within our data folder. As you can see in this CSV file, there are a total of 4,992 rows. These correspond to 4,992 individual convective rain cells. Each convective rain cell has its maximum rainfall intensity, along with its major and minor axis lengths. In today's exercise, we are interested in exploring the relationships among these three parameters, and whether it is possible to effectively simulate these relationships using a copula model. If so, this would be very helpful in our subsequent hydrological simulation and analysis. This could help us better capture the characteristics of convective rain events in the Birmingham area. Next, I will briefly introduce the key steps involved in our analysis. The first step is to analyze these three parameters to find the best fitting probability distribution for each. The second step is to analyze the correlation among the three parameters. We will use Kendall's TO and Spearman's RHO for this analysis, both of which are non-parametric measures of correlation. They analyze the rank-based relationships between the data. Their values range from 1 to 1. A value closer to 1 indicates a stronger negative correlation between the variables. A value closer to 1 signifies a stronger positive correlation, while a value near 0 suggests a weak correlation between the variables. Kendall's tau specifically focuses on the concordance or discordance in the orderings of two variables. For example, as the rainfall intensity increases, does the major axis of the rain cell also tend to increase? If this pattern holds in most cases, then Kendall's tau would be closer to 1, indicating a positive rank correlation. Spearman's RHO examines the overall trend between two variables, specifically whether they tend to increase or decrease together consistently. Kendall's tau and Spearman's RHO are particularly useful as they effectively capture nonlinear correlations between variables. Therefore, in copula analysis, they serve as important reference indicators for assessing dependence. In the third step, we will use the 5 copula models we just introduced to fit our observed data. Naturally, the fitting results may vary across different models, so we will also use visualization techniques to evaluate how effectively these copula models reproduce the correlations observed in our data. Next, we will use Python to execute these steps. First, we have prepared the materials for this analysis, including the necessary packages that need to be installed beforehand. Once the installation is complete, we will import the relevant functions from these packages. For copula analysis in Python, we primarily use the copula package, which offers a wide range of copula models and functions. Next, we can import the data. The first step is to identify suitable probability distributions for the 3 parameters. To accomplish this, we will perform distribution fitting, which involves finding the best fitting distribution for a given data set. Here we introduce a function called fit optimal distribution. This function allows us to input a data set and specify various probability distribution models, automatically selecting the most suitable one. In other words, it helps us choose the optimal distribution for the data and provides visualized plot results to assist in our assessment. Now let's utilize the maximum rainfall intensity data and experiment with this function. We need to provide 3 arguments to the function. The first is the data itself. The second argument includes our assumptions about the potentially suitable probability distributions for the data. Here I am specifying 3 candidate distributions, Weibull, gamma, and log normal. The third argument is the title for the generated plot. This title can be customized as desired. With these arguments provided, we can proceed to execute the function. The results indicate that the Weibull distribution is the most suitable for the maximum rainfall intensity data. It also displays the AIC, Akaike information criterion value for each fitted distribution, which helps determine the best fitting distribution. We will delve into the details of AIC later in the tutorial. Here, we also see a table displaying the fitting results, where you'll notice the term log likelihood, a concept likely covered in previous lessons. We often use log likelihood in statistical analysis as a basis for comparing the fit of different data distributions. When the log likelihood value is larger, it suggests a better correspondence between the model and the observed data. Conversely, a smaller AIC value indicates a better fit for the dataset. The figure also demonstrates the visualization comparison of 3 different probability distributions fitting result. Typically, visualization is the initial step in probability distribution fitting, allowing us to directly observe the fit and easily evaluate the results. Based on the visual representation, the Weibull distribution appears to be the most suitable, showing a good fit, especially in the tail region. Next, we can use a more structured approach to perform distribution fitting for all 3 parameters in the dataset. The first task is to identify suitable potential data distributions for each parameter. Next, we can prepare a dictionary to store the results and use a for loop to systematically record all the outcomes from the distribution fitting analysis. Next, we can execute this code to observe the results of the distribution fitting analysis. Here we can see that for the major axis, the log normal distribution provides the best fit. Both quantitatively and visually, this result appears ideal. Similarly, for the minor axis, the log normal distribution is also the most suitable. With that, we have completed the individual distribution fitting for all 3 parameters. Next, let's discuss the AIC method that we employed during the fitting analysis process. The AIC method is fundamentally based on the concept of maximum likelihood estimation, MLE. MLE should have been introduced in earlier lectures in this course, so we won't delve into the specifics here. In practice, we commonly use the MLE log likelihood to evaluate the performance of a statistical model. However, this method has a potential drawback. It doesn't explicitly account for model complexity. This means that if the model we use to fit the data has many parameters, it may lead to overfitting. In such cases, the model might primarily capture noise within the data rather than the underlying signal. Secondly, using only log likelihood for model selection can be unfair when comparing models with varying complexities. To address this issue, the AIC method was developed. Now let's examine the formula for AIC. The AIC formula is given by AIC anscherm 2k, 2, log likelihood, where k represents the number of parameters utilized in the statistical model. For instance, for the gamma distribution, its k value would be 3 because it is characterized by 3 parameters, alpha, beta, and gamma. AIC aims to penalize excessive model complexity by considering the number of parameters in the model. This allows us to balance the goodness of fit with the parsimony of the model. Returning to the AIC formula, our objective in model selection is to identify the model with the smallest AIC value. A lower AIC value suggests that the model provides a better fit to the observed data distribution. As demonstrated earlier, we utilized AIC to select the optimal individual probability distribution for each parameter. Similarly, we will also employ AIC as a criterion for selecting an appropriate copula model. With this, the first step of our analysis is complete. The second step involves examining the correlations among cell properties. As previously mentioned, we will utilize Kendall's tau and Spearman's RHO to evaluate these correlations. Here we introduce a function called pairplot example. This function generates a figure that encompasses three key pieces of information. Firstly, it shows the scatter plots of the joint distributions for each variable pair. Secondly, it presents the individual histograms of their marginal distributions. Lastly, it provides the values of Kendall's tau and Spearman's RHO for each pair of variables. We can start by executing the code and then scroll down to inspect the generated visualization. Let's briefly review the information in the plot. Here, Imax represents the maximum rainfall intensity of the convective cell. Axis-Maj denotes the length of the major axis of the rain cell. Aximin denotes the length of the minor axis of the rain cell. In the visualization, you can see that these three parameters exhibit interrelationships, which are statistically significant. The correlation between the major and minor axes is the strongest among the three pairs. Additionally, we can examine the specific patterns of these correlations, which are not strictly linear. This characteristic makes the dataset well suited for using copula to construct a statistical model. As you may recall, a crucial step in copula analysis involves applying the probability integral transform. This transformation maps the marginal distributions to a uniform distribution, which we can achieve using the pseudo-OBS function. The term pseudo-OBS refers to the transformed data in copula analysis, often called pseudo-observations. After applying this transformation, we can use the pairplot example function to visualize the distribution of the transformed data. The graph shows that the probability integral transform has successfully converted the marginal distributions into uniform distributions, mapped into a standardized space from 0 to 1. Additionally, you can observe the corresponding joint distributions between the transformed variables. This concludes our preliminary analysis of the relationships among the variables. The next step is to fit the copula models. To ensure clarity, we will reduce the dimensionality of our analysis from 3 to 2, focusing on the major and minor axes of the convective cells. With our variables selected, the next step is to fit the 5 copula models introduced earlier and analyze the results to identify the best model for our data. First, we need to initialize the copula models that we intend to fit. We must also specify the dimensionality of our data to the models, which is 2, since we are analyzing 2 variables. After initializing the copula models, the next step is to invoke the fit function. This function requires us to input the data that we want to analyze. The verbose argument controls output detail. When set to 0, it returns only essential statistic result without optimization details. The third argument, toPobs, indicates whether the function should automatically apply the probability integral transform to the input data. By default, toPobs is set to true, highlighting the need for the probability integral transform before fitting a copula model. Now, we can execute this code to fit the copula models to the transformed data. After the fitting process is complete, we introduce a function called summarize copula-fit. This function helps us extract the numerical results obtained from fitting the different copula models. It allows us to compare these results and determine which model is the most suitable for our data. Upon execution, the output shows that the most suitable model for our data is the Gumbel copula. The Gumbel copula has the highest log likelihood among the fitted models, indicating it provides the best fit to the data. The same conclusion can be drawn from the AIC values as well. We have identified the Gumbel copula as the best-fitting model for the joint distribution of the major and minor axes. Next, we will evaluate the performance of this fitted copula model. The evaluation method we will employ involves utilizing the fitted copula model to generate synthetic data. We can compare the generated data with the original observed data to see if the fitted model accurately reflects the observed distribution. While we could evaluate only the Gumbel copula as the best fitting model, we will include all fitted copula models for a more comprehensive analysis. For this evaluation, the generated data's sample size will match the length of the original observed data, facilitating a clearer visual comparison. Now, let's execute this code to generate the synthetic data. After data generation, we can proceed with visual comparison and analysis of the datasets. Here's the code for generating the visualization using the Bokeh package for interactive comparison. The plot displays 6 datasets, observed data and synthetic data from 5 copula models, each representing the joint distribution of generated samples. Each dataset in the plot includes its corresponding Kendall's tau value. Initially, all copula models except the Clayton copula show Kendall's tau values close to the observed value. However, closer inspection reveals noticeable differences between the observed and generated data. First, let's examine the observed data distribution, which shows a more pronounced upper tail dependence. This aligns with Gumbel copula properties, as the data generated from it also shows significant upper tail dependence. In contrast, the Frank copula captures moderate dependent structures and does not align well with the observed data. Thus far, our analysis has been conducted in the copula space defined by the uniform distributions from 0 to 1. However, we can further convert these uniform values back to the original numerical domain of the variables. This allows us to compare the generated data with the original observed data. To achieve this, we introduce a function called transform_uniform to marginal. This function utilizes the results from our first step, where we fitted the individual probability distributions to each variable. Using the percent point function, ppf, or quantile function, we can convert copula-generated values from 0 to 1 back to their original value ranges. These 5 lines of code convert each set of copula-generated samples, mapping them to the corresponding marginal distribution of each variable. Like our previous analysis, we can use visual methods to examine the distributions after this inverse transformation. As in the preceding analysis, the visualization will display a total of 6 datasets. The inverse transformation incorporates the marginal distributions, restoring the original scale and characteristics, so the displayed distributions reflect the original data distributions. In terms of the performance of the different copula, the results are consistent with our previous observations. After the inverse transformation, the Gumbel copula's distribution closely resembles the original observed data. It shows the best performance by AIC and visual comparison in the copula space, as evident in the visualization. We can also compare the student T copula, which shows a more dispersed distribution than the observed data, making it less ideal than the Gumbel copula. This visual comparison of the inverse transformed distributions concludes our analysis and tutorial on copula analysis. I hope this tutorial has provided you with a comprehensive understanding of copula and their applications in multivariate analysis. If you have any further questions, please feel free to contact us via email for clarification or further discussion. Thank you for your attention.